Welcome. So last video we have seen the different modes of fracture, about ductile and brittle fracture, and about the stress concentration, and also the next is impact testing or notch impact testing. So this testing technique is used to measure the impact energy required to fracture a material. So ductile and brittle are terms used to distinguish two extremes of fracture modes based on plastic deformation in wood before fracture occurs. So in order to distinguish the modes of fracture, the most common terms used are ductile and brittle fracture. So the three factors which aid from transition from ductile to brittle are first one is triaxial state of stress and low temperature and rapid rate of loading. So these three factors aid the transition from ductile to brittle. Since the brittle fracture is most unpredictable, it's been extended at a great extent. The notch will be introduced to simulate the conditions. So the impact testing techniques were used to find the fracture characteristics of the material. Okay, so there are generally two standards, ISOD and Charpy test, which are used to measure the impact energy. So the Charpy V-notch test is the most commonly used, and this is the apparatus. You can see in this figure, and this is the apparatus for making a V-notch impact test. Okay, the setup is like this. A weighted pendulum hammer will be released from a cock position at a fixed height H, and the specimen will be placed here at this position, and the specimen is provided with the V-notch. So a V-notch will be provided in the specimen, and it is used to simulate the conditions. Okay, so when this pendulum is released, it strikes and fractures the specimen at the notch. So fractures the specimen at the notch, and the notch will act as a point of stress concentration for the high velocity impact. So this pendulum, it continues its swing, reaching a maximum height h dash, which will be lower than the initial height h, and this will be a measure for the impact energy. Okay, so a notch increases the tendency for brittle fracture by four means: by producing a high local stresses, by introducing a triaxial state of stress, and by producing high local strain hardening and cracking, and by producing a local magnification to the strain rate. So the difference between a Charpy and ISOD test is the support given to the specimen, as you can see in this figure. So the support will, if the support is given like this, and it's made horizontal, and the V-notch is provided here, and the pendulum is impacted from this direction to hit this V-notch, and that arrangement is known as a Charpy test. Of a Charpy specimen, and if the specimen is placed like this in vertical manner and is impacted in this direction, this will be an ISOD specimen. So we can calculate the impact energy, and can be studied if we keep the sample at different temperatures. We can identify or find out whether the material has got a ductile to brittle transition based on the fracture made by the material. So next is ductile to so the aim of this Charpy test, Charpy and ISOD test, is to determine whether the material has experienced a ductile to a brittle transition. So next is a ductile to brittle transition temperature. So the ductile to brittle transition transition will be taking place at certain temperatures. That is, some material, it will behave as a ductile material at a high temperature, and as the temperature is decreased, it will lead to a transition to a brittle fracture mode. So somewhere in between, a transfer from ductile to brittle fracture will be taking place based on the change in the temperature. At high temperature, for example, a material such as an alloy of steel, it will act as a ductile material at high temperatures. But when the temperature is decreased, the material will undergo a brittle fracture. Brittle fracture mode. So the temperature at which there is a pronounced decrease in material's ability to absorb force without fracturing. At this point, the material transitions from ductile to brittle. So if at a particular temperature, if the material is not able to absorb the force without any fracture, without causing any fracture, we can say at this point the material transition has taken place. The material has transformed from a ductile to a brittle material, sort of brittle fracture. So that particular temperature is known as a ductile to brittle transition temperature, or a DBTT. Okay, so the energy absorbed during the notch impact is plotted as a function of temperature to know what temperature range the material fracture in a particular mode. So here you can see from this graph plotted against the fracture toughness against the temperature, and if the temperature is lowered, the impact energy will drop suddenly over a relatively lower temperature range. That is the mode of fracture will be brittle. So in metals, the ductile to brittle transition temperature is around 0.1 to 0.2 times the absolute melting temperature of the metal. So while in ceramics it's about 0.5 to 0.7 Tm. So these are the temperature range for the transition in metals and ceramics. So as we said, the primary functions of an ISOD and Charpy test is to determine whether or not the material has experienced a ductile to brittle transition when the decrease in the temperature. So at high temperature, the impact energy required will be a very large. So at high temperatures, the Charpy V notch impact energy, that is a CVN energy, is relatively large in correlation with the ductile mode of fracture. So at high temperatures, we will require a high impact energy to break the material, and the fracture will be a ductile mode of fracture. But as the temperature is lowered, the impact energy drops suddenly over a relatively narrow temperature range, below which the energy has a constant but small value, that is the mode of fracture is brittle. So as the temperature is lowered, the impact energy drops, so the fracture will be brittle. So the structures constructed from alloys will exhibit a ductile to brittle behavior. So the materials used should be above transition temperature to avoid a failure. So the material should be used above the transition temperature in order to avoid a failure of the material. So here we can see in this graph in impact energy versus temperature. In this graph we can see that the low strength metals and the most low strength metals and the most HCP metals does not experience any ductile to brittle transition, and they retain their high impact energy even with the decrease in the temperature. For example, this copper and nickel. So these low strength material, they retain their impact energy and will not undergo a ductile to brittle transition with the decrease in temperature. And for high strength materials, they are high steel or high strength materials, they are very brittle and are reflected by their impact energy. You can see this impact energy is very small. In an example for, we can say that in ships, in earlier periods, the main cause of ships is that main failure cause for ships were like that the ships will be broken into two pieces from the middle. So why this is happening? Because earlier the materials used to build a ship possess an adequate ductility at room temperature. But at a relatively low ambient temperature, the crack will be initiated or will be originated at some point of stress concentration, and this crack gets propagated in causing the failure of the material, and in turn this cracks propagates and continues to till it breaks the ship. So this is due to the transition of materials from ductile to a brittle fracture mode. So here we can see the fracture modes at different temperatures. So at a high temperature, the material which behave as a ductile fracture mode, and at a region of transition region, the material will be having an elastic plastic fracture mode in this ductile to brittle transformation region, and the material will undergo a brittle fracture at the lower temperatures, and it will be a linear elastic deformation in the material. So at a brittle fracture, the material will having a linear elastic deformation and an elastic plastic in the transformation region, and a ductile fracture at high temperatures. So not all metal alloys display a ductile to brittle transition. So those having an FCC crystal structure, including aluminum and copper-based alloys, remain ductile even at extremely low temperatures. So some FCC crystal structures, for example aluminum, copper, as we have seen in the earlier slide, that these metals or these alloys, it will not undergo any transition from ductile to brittle even at very low temperatures. So this transition is seen most commonly in BCC and HCP alloys. So for these materials, the transition temperature is sensitive to both alloy composition and microstructure. For example, the decreasing average grain size of the steel results in the lowering of transition temperature. Hence, refining the grain size both strengthens and toughens steels. That is, if there is a decrease in the average grain size, it will in turn result in the decrease in the transition temperature, and thus this decrease in transition temperature will lead to increasing in the strength and toughness of the material. So in order to avoid the transition of ductile to brittle, we can decrease the average grain size of steels, and it will result in lowering the transition temperature. So in contrast, increasing carbon content while increasing the strength of steel also raises the CV and transition of steels. It is as the carbon concentration is increased, the brittleness will increase, and the ductile to brittle transition temperature increase with the carbon concentration, but also it increases the brittleness of the steels. So next is a fatigue failure. Fatigue is another type of failure it's basically a type of failure in which occurs under fluctuating stress. So fatigue failure is the weakening of a material caused by cyclic loading that results in progressive and localized structural damage and the growth of cracks. So when a material is subjected to a dynamic and a fluctuating stress, for example in bridges, aircrafts or machine components, So under these conditions, that there is a chance of failure to happen, and at a stress lower than the tensile and yield strength of static load, this failure will be taking place. So once a fatigue crack has initiated, it will grow a small amount. It will grow a small amount with each loading cycle, and typically producing striations on some parts of the fracture surface. So the crack will be initiated and it will grow by each loading cycle, and typically and leading to a failure of the material. So the crack will continue to grow until it reaches a critical size, which occurs when the stress intensity factor of the crack exceeds the fracture toughness of the material, and producing a rapid propagation and typically complete fracture of the structure. So this crack will continue to grow, and the stress intensity fracture of the crack will exceed the fracture toughness, and thus generating a rapid propagation and typically leading to a complete failure of the structure. So the fatigue occurs at stresses that considerable smaller than the yield or tensile stress of the material. So also these are a very dangerous failure, because these failure also happens without any warning. So typically machine components machine components subjected to fatigue. So the common occurrence or the common examples of materials which undergo fatigue are the automobile crankshafts, bridges, aircrafts, landing gear. So these materials will undergo a fatigue failure. So next is stress cycles. So stress applied may be axial, torsional, bending in nature. So there are three stress time modes, and the first mode is a reversed stress cycle. So in this reverse stress cycle, the amplitude is symmetrical about the mean stress level. So the maximum tensile stress to max is so in the maximum tensile stress to maximum compressive stress, the amplitude will be symmetrical. And the next cycle is a repeated stress cycle. So in a repeated stress cycle, the maximum and minimum are asymmetrical value relative to the stress level. So repeated stress cycle in which the maximum and minimum stresses are asymmetrical relative to the zero stress level, and we can calculate the mean stress sigma m is equal to sigma max by sigma max plus sigma min by minimum by 2, and the range of stress sigma r is equal to sigma max minus sigma minimum. So the third stress time mode is a random stress cycle. So in this random stress cycle, the stress level is random in their amplitude. So there is no any particular cycle. So stress level will be random. So the fatigue failures can occur in both metallic and non-metallic materials, and are responsible for a large fraction of identifiable service failures of metals. So it can happen in both metallic and non-metallic materials, and you can recognize the fatigue failure from the appearance of the fracture surface. So this will be the fracture surface after a fatigue failure. So it will be having a region of origin and a fatigue zone, and the area where the final fracture will be taking place. So this will be the microstructure, and you can see here this will be the origin of the fatigue crack, and here will be having a burnished or a smooth surface near the origin, and we can see the beach marks, as you can see here in the we got the beach marks, which will be having a clamshell pattern, and the final region will be having a granular or a rough surface where the final fracture takes place. So this will be the appearance of a fracture surface which undergone a fatigue failure. So this fatigue failure can expand the stages into four. There will be a fourth stage. The first stage is crack initiation, and the second stage is slip band crack growth, or the crack growth stage, from the crack growth stage, and the third stage is crack growth on planes of high tensile stress, and finally ductile fracture. So first stage is crack initiation or crack nucleation. It includes the early development of fatigue damage, and it can be removed by a suitable thermal annealing process. And the second stage, or stage 1 of the crack growth, is in slip band crack growth, and it involves the deepening of initial crack on planes of high shear stress. And next is the crack growth on planes of high tensile stress, and it involves the growth of crack in direction normal to the maximum tensile stress. And finally, the fourth stage is final ductile fracture, and it occurs when the crack reaches a size so that the remaining cross section cannot support the applied load. So finally, the material will be split into two more pieces. So fatigue crack growth stage 1 versus stage 2. So the second stage is crack growth, and it happens in two stages, stage 1 and stage 2. The first stage is the stress involved in stage 1 is shear stress, but in the stage 2 is tensile stress, and the crystallographic orientation will be there for stage 1, and there will not be any crystallographic orientation for stage 2, and the crack propagation rate will be low for stage 1, and it will be high in the case of stage 2, and the slip will be happening on a single slip planes in stage 1, and it will be taking place in multi-slip planes in stage 2. And stage 1 will be having less features, and we can see visible striations on the stage 2 of the fatigue crack growth stage. So these are the two stages in the crack growth. Crack growth happens in first stage, two stages, and the first stage is crack growth on slip band, and second is crack growth on planes of high tensile stress. So this here we can see the difference between a static load and cyclic load. So the static load is when static load is applied, the material will deform and it will be looking like this, and in the case of cyclic load, we can see with some extrusions and intrusions in the materials. So this due to repeated loading or a cyclic loading, there will be development of intrusions and extrusions. So fatigue failure, the three basic requisites for the occurrence of fatigue fracture. First one is the maximum tensile stress of a sufficiently high value, and the second requisite is a large enough variation or fluctuation in the applied stress, and a third one is a sufficiently large number of cycles of applied stress. So these three processes will be required for the occurrence of a fatigue fracture. So first one is a maximum tensile stress, and next is variation or fluctuation on the applied stress, and third is a large number of cycles of applied stress. So the stress cycles that cause fatigue failure are characterized using the following parameters. So the first one is a range of stress sigma r is equal to sigma max by sigma minimum, and the alternating stress sigma a is given by sigma r by 2, and which will be equal to sigma max minus sigma minimum by 2, and the mean stress is sigma m is equal to sigma max plus sigma minimum by 2, and the stress ratio will be r is equal to sigma minimum by sigma max, and the amplitude ratio a is equal to sigma a by sigma m, where sigma is the alternating stress, and which will be equal to 1 minus r by 1 plus r. Fatigue testing. So cyclic stress is the distribution of forces that change over time in a repetitive fashion. So when cyclic stresses are applied to a material, even though the stresses do not cause plastic deformation, the material may fail due to fatigue. When these cyclic stresses, when it is applied to a material, the material will fail due to fatigue. Here we can see a test apparatus which is used to simulate the possible service stress conditions during a rotation. So a specimen will be placed as shown here in between two bearings, and it will be subjected to rotation. So during rotation, the lowest surface of the specimen will be subjected to a tensile stress, and the upper surface will be subjected to a compressive stress. So a series of tests will be subjected to the specimen at a relatively larger maximum stress amplitude, and the number of cycles to failure will be counted, and the data observed will be plotted on a stress versus a number of cycles curve, that is an SN curve, and to determine when the failure or the fatigue failure of the material will be taking place. So this is an ascent curve, and this curve plots the number of cycles required for failure at a given stress amplitude. So the number of cycles will be plotted on the x-axis, and the stress amplitude on the y-axis. So here we can see two types of materials, a non-ferrous material and a ferrous material. And in non-ferrous material, with the increase in number of cycles, the minimum stress amplitude required will be keep on decreasing. So as the number of cycles increase, the stress required to failure of the material will be decreasing. So at minimum stress, failure will be taking place at with the increase in the number of cycles. Okay, so if we have a lower stress amplitude, the number of cycles to failure will be increasing. So whereas in the case of ferrous material, it will not fail for a number of cycles under limited stress condition. So in this non-ferrous material, we can say if the material at 10 to the power 5 cycle, the failure will be taking place at a particular higher stress, and then at a cycle 10 to the power 7, which is more than the 10 to the power 5, the failure will be taking place at a stress somewhere around here. So but in the case of a ferrous metal, it will not fail for the number of cycles under limited stress conditions. So here we have a fatigue or an endurance limit. So the stress level below which the fatigue failure will not fail with the increase in number of cycles, so that level is known as the fatigue or an endurance limit. So below this level, the fatigue failure will not be taking place with the increase in number of cycles. So the parameters on the fatigue parameters on SN curves, the material fails under fatigue mode at higher number of stress cycles if stress applied is lower. So after limiting stress, the ferrous material won't fail for any number of cycles. This limiting stress is called a fatigue limit or an endurance limit. And for non-ferrous materials, there is no particular limiting stress. That is, as the stress reduces, the number of cycles to failure keeps on increasing. So hence the stress corresponding to 10 to the power 7 cycles is considered as a characteristic of material and known as a fatigue strength. So the number of cycles is called the fatigue life. So the endurance ratio is the ratio of the fatigue stress to the tensile stress of a material. So for most materials, it is in the range of 0.4 to 0.5. So here are the factors affecting the fatigue strength. So factors are type and nature of loading. Next is the size of component and stress or strain distribution, and the surface finish and directional properties, stress or strain concentrations, mean stress or strain, that is, it means the increase in the mean stress, it will lead to decrease in the fatigue life. So next is environmental effects, then metallurgical factors and material properties, and strain rate and frequency effects. So for an assignment you have to explain each of these factors in detail. So that's about fatigue failure. So in the next class we will be discussing about creep.